Yeah, thank you so much, Juan, for the nice introduction. So, yeah, I would like to talk about enabling cloud infrastructures and cloud technologies for space. Um, um, I was listening with great interest to the keynote presentation of Scott today. Did briefly touch on that topic. So, if this made you curious, here's the full story. So, yeah, let's start with our motivation. Let's start with our general focus at the moment at D3TN. So, at the moment, we are focusing on two topics. So, our main motivation, of course, over several years has been always space, and as we are at STINT, this is also the focus of this presentation. But a yeah, I must say we had a second area of interest that emerged in the last couple of years, because we also have some background in conventional cloud infrastructures and distributed systems on Earth. And the second area of interest for us is called air-gapped systems. So this is basically infrastructure that is not connected to the terrestrial internet and has to be operated in a different manner. Because of that, yeah, for example, because it's operating critical infrastructures like power supply companies, stuff like that. And we saw that both areas basically use a similar mode of operation for their systems, which means there are like configuration changes have to be performed often manually. You plan everything well in advance. You have a sophisticated planning of your changes to the system, of your upgrades of the software and so on. And oftentimes you also individually manage all your assets. Also, obviously, great care has to be taken which data goes in and out. For those air-gapped systems, typically you don't want any data to get out, and at least any malicious data not to come in. And well, this has to be seen in contrast to most modern cloud computing infrastructure, where, well, taking a look at the cloud technology landscape, yeah, basically it's very different. It's a very different mode of operation. You have ubiquitous, cost-effective access to all services and data. You have APIs everywhere. You can just fire some request for one or two or thousands of resources, of computing resources, of storage, of whatever, and you will get that. The hyperscalers will deliver. You have a very scalable, flexible, rapid access to all the infrastructure. Everything is highly available. Everything is load balanced, fault tolerant. The infrastructure will automatically react if anything fails, and everything is still working. So all while many users are sharing the same infrastructures, but that don't actually, most of the time they don't know of each other. I mean, the goal is that they don't influence each other, even though they are running on the same physical infrastructure. When you want to transfer this to space, well, there are some issues. There are some very serious limitations in space. And first and foremost, this is because you don't have continuous low latency connectivity, as we all know. And all those modern cloud technologies have been developed under the assumption that there is continuous low latency connectivity. And well, a second point that I won't touch too much on today, but which is also very important, which is why I'm listing here, is that high complexity and energy demand of the systems. So, well, as I said, we would like to mostly focus on the first point. Continuous low latency connectivity is not. We have the challenges, we have disruptions, we have delays. As we are at STINT, we know the solution is delay and disruption tolerant networking. But the question that we are asking ourselves is it possible to somehow make use also of some of the modern cloud native execution environments in such a context, in such a D3TN environment? And well, this is exactly the focus of our Dark Soul project that Scott was already mentioned in the morning, where we touch on all the layers of the system. Basically, we are taking a look at the infrastructure layer, we're taking a look at the execution environment, at the platform, and also at how to operate applications and how to make them communicate with each other. So at the moment, we are like right in the middle of the project timeline. We have done some initial analysis of the general technologies, of the general setup, and we have derived an architecture, which I would like to touch on the next couple of slides. And yeah, then basically we have 1 year left, and I will also briefly touch on the topics we would like to explore in that. Okay, but yeah, let's take a look at this picture. This is basically our vision of how a space cloud infrastructure might look like in the future. We are making one very central assumption here, and that is that we have groups of nodes that are continuously interconnected using low latency links. And this is what we call the clusters, the space cloud clusters. This is the red boxes here. And for these, we can assume that we can use regular IP networking inside the cluster. So we don't have to adapt anything that runs inside such a cluster and only communicates within it. And in addition to that, we have episodic links. We have delay and disruption tolerant communication, which is those dashed lines. And this only usually happens between clusters or between clusters and operators. Or clients basically that connect to these clusters externally. There also may be something like an isolated cluster, which is this example of air-gapped infrastructures where we don't have any links at all to the outside. So what are we exploring currently? We are exploring to run a technology called Kubernetes. So to use Kubernetes to run these space cloud clusters. Why Kubernetes? Well, it's a widely used technology. It's a container orchestration platform that is production ready, that is used in the industry for quite a long time already, that is powering the infrastructure of several large-scale companies, and gets more and more important, basically. There is also lots of tools and integrations available for Kubernetes. Most modern software stacks support it. Most, at least, can be deployed somehow in Kubernetes or have some extensions to support it. And also, it uses containers. It orchestrates containers. Compared to using virtual machines, which was oftentimes done like in the past. This has lower overhead and higher flexibility. Also, Kubernetes brings some, I would say, desirable properties with it, which is that you basically declare your infrastructure, that you have a declarative configuration of everything. And based on that, it performs quite advanced scheduling and management, and also supports like shifting workloads. If anything breaks, it has self-healing properties, has integrated secret and configuration management, scales very well, is very extensible, and yeah, well, this last point of extensibility is also what we are yeah, basically leveraging in our dark soul project. Before talking about specific aspects that we are adjusting and extending in Kubernetes, I would like to briefly talk about our general approach, how we want to do this, and yeah, basically some two general constraints we set, two general assumptions we make basically that we want to yeah, fulfill when doing these extensions to the infrastructure. First of all, we do not want to break up the clusters. We do not want to substantially change the proven existing technology, in this case Kubernetes. We don't want to hack DTN into it, right? We don't want to yeah, change the central software component so that I am able to put a DTN link somewhere inside the cluster, because this would be a beast regarding complexity, and also we would need to somehow, well, adapt the code of this upstream project, and well, either get our modifications into the upstream project, which I'm not too confident is possible at least at such an early stage, and with our current power and effort we can put into that. And well, the second option would be to fork it and maintain a DTN enabled copy of Kubernetes, and this is also just not possible. The second central aspect, the second central point that we basically want to not do is hiding the DTN aspect. We always want to make applications and users aware that they are communicating over a DTN link. We don't want to somehow put DTN somewhere in the middle of a link where the applications on other sites assume that they are using IP connectivity, because in most cases applications are developed based on the assumption that there will be, if there is a response to your request, it will come in a timely manner. And if this expectation is not fulfilled, things are going to break. So we don't want to make the DTN aspect implicit. We plan to offer additional APIs and interfaces that the applications and users have to use, basically have to choose to use, so that they are that they are aware that they are communicating over a DTN. We don't want to make it inconvenient. Of course, it has to be convenient to adapt applications, and we can always think about stuff like introducing specific application layer proxies or application adaptation. If we know the application protocol, basically, this is I think also related to Rick's talk yesterday. We can do a whole lot of further things to make the integration easy. But at this point, we are only taking a look at the transport basically, and we don't want to make the DTN aspect transparent in there. And so, in general, the goal for us is to implement sensible extensions to solve the specific problems of cluster external DTN communication. So, how do they look? How do they look like? Let's briefly take a look at an example space cloud cluster here. We have a very simplified depiction of a Kubernetes cluster that is deployed on 3 physical nodes. Shown as these boxes here with a small satellite icon. We have one node running the control plane components, the scheduler, the database, the API, and we have two two physical machines, here two satellites in this case, executing the worker nodes of Kubernetes that will run the actual space cloud workloads. As we are assuming that inside the cluster we have low latency connectivity, we can have regular IP links there, we can have all the API accesses run basically as usual. However, there is like two important points on where external connectivity comes into place. And the first one is this part here. It's labeled user or client API, and this is for communicating with the platform, with the cluster infrastructure, basically for operators and administrators to tell our space cloud cluster, I would like to deploy this and that service and this and that application with this and that images and this and that configuration. And well, usually you will not have your operator sitting next to your satellite. So we somehow need to make this delay interruption tolerant. And for this, we are introducing a component that is called the D-proxy or Dark-Soul proxy that sits between this API and the users of this API. And that, basically packs together all the data needed to execute a specific request. So we will see an example on the next slide that packs together all the data that is needed, for example, to deploy a specific set of containers with a specific set of images. The images are also put together with this and are then packed into a DTN bundle, are sent through the DTN link, and are then basically here by the second part of this component fired against the API so that the service is deployed in the infrastructure. So this is an example we are currently working on, and Scott already showed this in the morning. It's quite interesting to us to get this also working with state-of-the-art management tooling, and one important application lifecycle management tooling for Kubernetes is Helm. And we plan to build an extension to that. We have a very early prototype already to add like a DTN command to that, where we can deploy these Helm charts by basically packing together all their dependencies and everything into a DTN bundle, transmitted through our DTN protocol implementation, and then it reaches the cluster where we have another component called the application lifecycle management controller, and this one then executes it in the space of the cluster. So this is what we are working on currently, and we will hopefully have this ready over the next year, and maybe we can present it at the next STINT. A second very important point that we have to offer in the space cloud infrastructure is, the communication between the applications. So the D-proxy is caring about the communication with the cluster, with the cluster API, but of course we also want to execute applications inside the cluster, and probably they will need to be accessed also externally, or they somehow want to communicate externally as well. So we need something to offer them delay tolerant communication capabilities as well. And for this, we are developing a second component that is called a D-gate, or Dark-Soul gateway. And that's basically for the Kubernetes cluster. It's a Kubernetes resource that is deployed inside the cluster along with the application, and that has some facilities to exchange reachability information with other D-gate instances. So to automatically, when it is deployed, make other other instances of the V-Gate reachable so that applications don't have to care about contact plans and stuff like that. And of course, this is the most central aspect. So the distribution of this endpoint reachability information somehow has to be realized. And for that, we are currently working on two basic mechanisms. First of all, we want to allow it that a space cloud cluster is also connected to some IP network. I mean, if you remember the figure I showed at the beginning, it can also run on Earth. It has DTN capabilities and can communicate through a DTN that is attached, but it can also have a planetary IP-based network attached to it. And we think that we need two different, or we should use two different mechanisms for distributing this reachability, this basically routing information for both IP-based networks and on the other hand, DTN networks. And the first aspect, we are planning to take care of this by integrating DTN reachability information into an IP routing protocol, specifically BGP, the Border Gateway Protocol. And we will have a paper presentation about this today. Theo will present this his paper on exactly that topic. I think it's the fifth paper presentation, so in the second session today. So stay tuned for that. On the other hand, we need something that distributes the reachability information over the DTN link. And this is like the second aspect we plan to now touch on in the remaining project year. So we are currently developing concepts for that and discussing how to tackle it. Specifically, we want to take a look at DTN discovery protocols. For example, the SAND neighbor discovery protocol is currently an IETF draft specification. Okay, if you have been waiting for the AI buzzword in this talk, now it comes. We have developed an example application to validate the V-Gate, and this is a very basic machine learning pipeline with 4 phases. We assume that we have some high-powered infrastructure on Earth that can do some model training based on some image analysis. And based on that, the pre-trained model is distributed to our space cloud using the V-Gate, where it is used for performing inference based on pictures that have been taken by the space assets to decide whether or not to send them to Earth, basically, and to reduce the amount of data that has to be transmitted, for example. And in the end, after this inference process has concluded, the selected data is collected and can be fed back to iterate the model training process to improve our prediction as well. We have implemented this prototypically in a test setup. We have a small demo. However, this is currently still using console applications. We don't have a nice UI for that. If you're interested afterwards, I have a screencast. This would take way too long now. So I brought 2 screenshots from it and labeled it a bit. So on the left-hand side, I know the text is very small, but it doesn't matter. On the left-hand side, we have 2 console windows that are connected to our space cloud cluster. We have here the output of kubectl showing that we have an instance of our gateway running. We have an instance of a bundle protocol agent running. And on the right-hand side, we have our operator console, where we also have a bundle protocol agent, some configuration console window, and then this is like the interface to our test setup. where the operator now has requested to send the weights to the Space Cloud cluster and by that trigger the inference. And the cluster has received the signal and then basically runs process and sends back the analyzed picture, which is here a nice picture from Mars with something interesting that has been inferred. So it is sent back to Earth over the D3TN link and appears in this directory, and we can the operator console. So yeah, that's the current status of the demo app for the V-Gate. So we were able to show that it's working based on that. And yeah, based on that, we can say, in general, we can make cloud technologies work in space. We can do that without substantial changes to the internal workings of the technologies, which was very important to us. But yeah, obviously there is still a long way to go. Still a lot of topics. Some of them are listed below that we have to somehow tackle. In the near term, we see some valuable applications also on Earth in this domain of air-gapped systems. But yeah, in the long run, I think it will become a viable tool to have also this cloud-native technologies be ready to be used in future space missions. So what are we working on currently in the remaining project here? First of all, we have an ongoing effort at modeling the infrastructure and an abstraction to allow, for example, simplified configuration and transfers between different instances, between different technologies. There is also a paper on that presented by Anastasia today in the first session. Then we are working on integrating application lifecycle management tooling, this helm example that I showed. And we are working on integrating D3TN discovery mechanisms. After this project, maybe for a follow-up, we have not decided yet. We have to touch on also very important topics that are out of scope for this first research iteration. For example, we don't care about security at the moment, which is a very important point. I know, Rick. And of course, we also need key management for that. So this is one of the first things we're going to work on afterwards. Monitoring and observability is also extremely important in modern cloud infrastructures. You really want to know what broke when something breaks, right? You want to get the logs, you want to get the performance data and so on. This has to be supported also for the space cloud. The third aspect is load balancing and high availability. The infrastructure we are using already has quite some nice properties and quite some nice facilities for that. However, of course, we also need to make our extensions highly available. And yeah, we plan to explore, for example, also load balancing for the D3TN link. And yeah, last but not least, energy efficiency is also key for space applications. And by that, I would like to thank you very much for listening.